All right, 13.8, we're going to classify quadrilaterals on a coordinate plane. And after today, you'll be able to use coordinate geometry to classify quadrilaterals based upon their properties in a mathematical context. And you'll be able to draw quadrilaterals on a coordinate plane, given the definitions, properties, and theorems, and probably some equations and stuff too. All right. Before we dive right into that, let's review some quadrilaterals from Unit 8 that we all learned and stuff. Okay, so I guess I'll just do it like this. Maybe I should turn it sideways and zoom out a little. No, I'll start at the top like that. All right, so remember we have a basic quadrilateral. Start with green. The basic quadrilateral, right, can be any four shape. That's not a good one. It can be any, this. There we go. I'll do that over. All right, so any quadrilateral is just a shape with four sides. Any particular shape with four sides, doesn't have to have any reason or rhyme. It is just a quadrilateral. Has four sides, right? This is a quadrilateral. Quadrilateral. It has four sides, four angles, and the measure of those four angles equal 360 degrees inside. That is just a basic quadrilateral. Okay. Well, you can break those down. Those can be classified into two. Break those down into I guess three major types. Okay. Let's break those down into three major types. Okay. Depending on a couple characteristics. All right. We'll break it down into a parallelogram, we're going to say if it has no parallel lines, only one set of parallel lines, or it has two sets of parallel lines. Okay. Good morning. Sorry about that. Okay, if it has no sets of parallel lines, okay, but it has congruent sides. Okay, two sets of congruent sides. Okay, so let's draw that. Two sets of congruent sides. Okay, let's draw that. So we have no parallel lines, but two sets of congruent sides. All right, so we have one like this, one like this. Those are congruent. And some like this, some like this. Nothing parallel. Two sets of congruent sides. We have ourselves a kite. Okay, and as a byproduct of that, that kite has diagonals which meet at 90 degrees. And those diagonals are perpendicular, and this line segment and this line segment are congruent. Okay, so that is a kite. Okay, it's got no parallel lines, two sets of congruent sides. One of the diagonals is bisected by the other diagonal, resulting in two congruent parts of one of those diagonals, and 90-degree angle, which which is, parallel bisector inside there. Okay? And then over here we have one set of congruent lines, and or parallel lines, and that's it. Just one set of parallel lines. All right, so let's set maybe make it pink. Yeah, let's go with pink. So one set of parallel lines, right? One like this, another one like this, for instance, and then the other set is just, whatever. Maybe it's like this and like this. That's just gonna be too long. Maybe it's like this. Not parallel lines. Make it like this. Right, this is trapezoid. Trapezoid. Okay? And in a trapezoid, we have a, remember we have the midpoint thing, right? We have this midpoint thing here, where this was what did we call this? Right, this midpoint here. If we took this midline, if this is a midpoint of this, and this is the midpoint of this line here is going to be 2 times the sum of this line and this line, right? And then this is the altitude right here, if you remember all those different things. So if this was A, and this was B, and this was C, and this was D, right, the relationship, and this was MP, right, for midpoints, right? So line MP, two MPs equaled A, B plus C, D. Move that over a little. Equaled A, B plus C, D. Or it's just an average. You could also just say this plus this is the average of this and this, right? Another way to look at that, okay? And then if I expanded this even longer, even more, and I said, hey, these line segments are congruent, right? Then I have myself an isosceles trapezoid. So this guy is congruent to this guy and this guy. These are all congruent. Congruent doesn't look like it. Did the best I could. But this is still the same, right? Same. This is an isosceles. It's a trapezoid. This is an isosceles trapezoid. Isosceles trapezoid. Right, and an isosceles trapezoid, this angle and this angle, these angles are congruent. These angles are congruent, and this angle plus this angle equals 180 degrees. Okay, so that is some useful information there. Okay, but those are the different triangles or trapezoids there. Okay, so then we have the 2 sets of parallel lines. Let me pause and get another color. Okay, I have 2 sets of parallel lines. We'll say this is a set here, and this is a set here, and this is a set here, and this is a set here. Let me fix it a little. find myself a parallelogram. Right? These are parallel, these are parallel, this is parallel, and this is parallel. And there's a bunch of properties about a parallelogram, right, that I can remember, right? These line segments are congruent. This is a parallelogram. Okay, parallelogram. These two line segments are congruent, and these two line segments are congruent. In a parallelogram, these line segments, or these angles are congruent, these angles are congruent. So that's helpful. Right, and then you have the, that's fine, I'll just keep that. And then you have two of these, right? You have these angles, these diagonals are congruent, okay? And if these diagonals are congruent, bisectors, this and that are equal, and this and that are equal, okay? So that's a different way to look at parallelogram, or that's some real quick review on parallelograms. Okay, parallelograms can be broken down even further. Okay, if your parallelograms, there's two ways to break down these parallelograms, okay, based upon their angle measures or their line segments. Okay, so if the hold on, how do I want to say this? Okay, so if the angle measures are all equal, so 90-degree angles, all 90 degrees, right? It squares this all up. Right, now you have yourself something of like a rectangle. Have yourself a rectangle. Yeah, so all these are now equal. All the angle measures are equal. Okay. Still have this line segment. This is a rectangle. This line segment and this line segment are still congruent, and that line segment and that line segment are still congruent. Now you have these line segments are equal, right? Both of those are the same length, okay? And all of these lengths are the same. So everything is the same inside of there, okay? If you have all of the line segments same length, right, but no 90-degree angles, okay? They're not on the outside, so you have like something like this. I can measure that. Make that 2. Make this 2. Is 2. 2-ish. That's going to be harder to do. That 2. Okay, so we'll just say that all of these are the same length. Okay, that is a rhombus. Okay, so the rhombus has 4 equal sides, right? But none of these angles are 90 degrees. Okay. However, the diagonals do meet at a 90-degree angle. Okay, so those diagonals there meet at a 90-degree angle. So that will help you remember that. If you combine these two, right, you make yourself a square. So square has all the same angles, all the same lengths, and all the diagonals are all the same, and they meet at 90-degree angles on the inside too. Right. Everything about a square is indeed square. Okay, so there's a review on all of the quadrilaterals. Okay, let me zoom out so you can zoom out. Zoom out. So maybe you can kind of see all of that. All right. So anyway, we pause this and get ready for the next part. Okay, so here I have a quadrilateral. We'll call it RQPT. Quadrilateral RQPT with the points 1, 8, 8, 4, 4, -3, and 3, -1. And we want to figure out what type of, if we can classify this quadrilateral other than a regular quadrilateral. Right, so we got to figure out a couple things. One, are the line segments the same length? And are the slopes the same? Are there any perpendicular lines, meaning are these angles 90 degrees or anything like that? So let's figure out the lengths of each one of these line segments. We've got to know change in x and the change in y of each. Right, so let's figure out the change in x, the change in y, and take the square root of each one of those, or square them, take the square root of the sum, and that'll be the length. That's just Pythagorean's theorem, right? This is a triangle. We've done that by now, so let's do that, right? The absolute value, well, let's do it in a different color. Well, we do it in a different color so it really pops. So the lengths of these really pop, okay? So we'll turn this sideways and do the lengths in pink. How about that? All right, so our change in x, all right, goes from 1, change in x goes from 1 to 8, so that's 7 squared. So that's 7 squared. So 7 squared is 49. Plus our change in y is 8 to 4 squared. So that 8 to 4 squared is 16. 16. So 49 is 16. 49 plus 16 is 65. It's going to be the square root of 65. So this is the square root of 65. Okay? So let's do this one. This is going to be the square root. I'll flip it sideways. Whatever. Square root of my change in x is 8 to 4. All right, that's going to be the square. So the difference between 8 and 4 is 4. That's going to be 16. Okay, my difference between 4 and -3. What's the difference between 4 minus 3 negative is 7. Okay, 7 squared is 49. So again, it's going to be the square root of 65. Okay, looking good so far. Okay, so how about this one? This is going to be -3 and 4. If I change in x, -3 and 4. Okay, so 3 negative minus 4. So my change in x is -7. I'm going to square that. That's 49. That's going to be the square root of 49 plus my change in y is going to do -1 minus 3 negative is -4 squared is 16. So it's -16 squared is 16. So it's going to be plus 16. So this is going to be square root of 65. Okay, it looks like our lengths are all coming out to be the same. What about this one? What about this one? This is going to be the square root, our 1 value. So it's going to be 1 minus 3 minus -3. So 1 minus 3 negative equals 4. Squared is 16. 1 minus 3 squared is 1 minus 3 is 4, squared is 16, and we're going to have 1, 8 minus 1 squared is 7, 8 minus 1 is 7, squared is 49. So it's again going to be equals the square root of 65. Okay, well, they're all the square root of 65, whatever that is. Now what's 65? 65 divided by 5 is 13, so you can't really reduce square root of 65 to anything. All right, so they're all the square root of 65. Okay, so these are all the same length. Okay, now the question is, are these perpendicular, making them a 90-degree angle? Well, we got to figure out what is the slope. What is the slope of these? Okay, well, what's the slope of, let's do green. What is the slope of RT? So RT's slope, remember it's a change in y over the change in x. Okay, so what is the change in y? The change in y, we'll go with this, from this, it's going to be positive. It's going up, right? So it's going to be positive, right? So it's going to be, well, it's going to be 1, or sorry, the change in y is 7, right? It went from 1 to 8, so it's 7. Okay, so it's positive, and then our x is -3 to 1, so that's 4. So it's 7/4. Okay, so how about our Q slope? Our Q slope, change in y over change in x, it's going to be negative. It's going to be negative. The change in r is 7. And the change in y, excuse me, was 8 to 4. Not 7. What am I thinking? It's 4. It's 4. And change in x is 7. Okay, well, that is the negative reciprocal. So this is a 90-degree angle. Okay, well, that's pretty cool. That's a 90-degree angle. How about this one? What is the slope of QP? QP's slope. QP's slope is change in y. Change in y. You can't see it. Change in y over the change in x. Okay, well, it's going to be positive. The slope is positive, so it's going up. Okay, so this is a positive slope. And our positive slope is going to be, our change in y is 7. You guessed it, change in x is 4. And you guessed it again, it is 90 degrees. Right, so if this is a parallelogram, you can already say, right, these are going to be 90 degrees, right? Yeah, it looks like we got a square here. Okay, looks like we have a square. But what else is it, right? And if it's a square, it's also a rhombus, it's also a rectangle, it's also a parallelogram. But you could also, what if you wanted to figure out the length of the diagonal, right? It'd be the same. It would be the same thing, right? If I want to figure out the length of the diagonal here, right? It would just be the square root of your changes in x. So it goes from, let's start that. Let's do your change, how far is the distance from your x's? Well, it's 8 minus 3 negative, which is 11. 11 squared. Your change in y is 3. So squared. So 121. I'm sorry, 11 squared plus 3 squared is 9. Get the square root of that. Also, square root. This is the square root of 130. In case you need to figure out the diagonal for some reason. And then the slope would be the same thing as we did here. Okay? So hopefully that helps and makes sense. And you use the same process for any type of quadrilateral given to you, and use what you know about quadrilaterals to prove or disprove if a quadrilateral is any type of quadrilateral, just using slopes and perpendicular lines and lengths of lines. So that's how you do it. Hopefully that helps.